You guys, let's roll. So what we're doing is the following. Last time we talked about interrupts, exceptions, and we know all the machinery which is required to process an interrupt, right? So, and we started talking about system calls, and the machinery to process a system call is exactly the same. When I say machinery, I mean like it goes through exactly the same interrupt descriptor table, very similar to how you would handle an interrupt, right? You handle a system call. And what we did last time, we looked at the pass of an interrupt through the kernel, right? And specifically, we know that it goes on like lands on vector. If it's a system call, it lands on vector 64 because the way we invoke a system call in x86 is int ox40, and this 40 is number 64. And for each interrupt, we have a separate assembly function. Who can tell me why do we have this separate assembly entry function for each interrupt? What's the idea? Why can't we land on a single entry? I'll be asking you this on the exam. When is the midterm already?
Is it because like not all interrupts can be accessed by like you want to have maybe we don't want some interrupts to be directly called from the user code?
No, that's not it. Well, I'll ask you again in a second how we prevent user code from calling all the interrupts. Why do we have, remember, okay, I can roll back a little bit forward here, right? Backward, sorry. So every time an interrupt starts, right? The interrupt starts on this function, sorry, which has this cryptic name, vector64, vector1, vector2. Why is that? Why can't we create an interrupt descriptor table which will have all the entries which point to one single generic int handler, for example? Why can't we do this? Why can't we just say, look, like after all, we know what to do. We have to save all the registers, then maybe process a system call or maybe process a timer. Why do we need to create the separate entry for each interrupt? Like, for example, vector 32, vector 16, vector 31. Why are we doing this?
Because some interrupts need arguments, and we need to format those arguments for the function calls for the interrupt handlers. Like the differences between different interrupt calls. Is it because of this?
Yeah, so Dominic has an answer in the chat. So he says that because we want to differentiate between interrupts. Correct, because really the hardware doesn't set a special register saying, okay, I'm delivering interrupt number 15. So, and the only way to save it is essentially as early in the interrupt handler to push the number. And then later on, you can look at this number and say, look, I'm really like, I'm processing interrupt number 64. That's why each interrupt has like we can call it a prologue, right? So this assembly sequence, which essentially first pushes the interrupt number on the stack and then goes to a generic function, which is called traps or trap, right? Which dispatches all the interrupts in a single function, right? But later on, you can distinguish it because you already have this number, right? Okay, I just wanted to make sure that we understand this. And okay, let me ask you another question. So since you brought it up, so how do we stop user code from invoking an instruction, something like int 15? I forgot which one is page fault.
The GD, like there's a flag on the interrupt vector which ring level can access it.
Correct, right? So both Dominic and you have a correct answer. Very good. So essentially, there is a flag which is called which designates the descriptor privilege level, which designates which privilege level can invoke this function and which cannot, right? And typically, we only allow user to invoke the interrupt which is responsible for the system call, right? Int x40 or in hex it's int 64, right? In this entry in the interrupt descriptor table, the privilege level is set to 3, so the user can freely invoke this function, right? Okay, since we are on this, are there any questions about interrupts? It's very important to understand this machinery. And in fact, the next homework will be about interrupts. ask now. I mean, all these simple questions, which are not really like, which seem trivial. Yeah, go ahead.
One question I have, like you were saying, in order to, can't we differentiate like type of interrupt by making, like following some kind of a convention where user process puts the interrupt call in like an EAX register or something and calls a generic interrupt, and from there we can pick up from the EAX register which interrupt is called and then process it?
That would be possible, but it's only possible for an interrupt which is invoked by the user code, right? And this is specifically how we distinguish between different system calls, like sysopen, sysread, syswrite, right? But if, for example, you do a division instruction and you're suddenly dividing by 0, right? Like this immediately lands you on the interrupt descriptor table, just because the hardware says, okay, like I don't know what to do in this case, right? And here you have to say something like vector, whatever number x-axis is the number for the division by 0, and then you will push this s x, and then later on you will be able to distinguish that it's really division by 0. The hardware, you will know the interrupt, you will know the instruction pointer which caused the interrupt, right? Because you can look it up on the stack, but you don't know whether it was maybe it was a page fault, maybe it was division by 0, maybe it was something else, right? So it's convenient to know the number.
Got it.
Okay, good. X40 corresponds to vector 64. I believe so. I think 40 is actually the number, right? Python or OX40. Yeah, it's just hexadecimal for 64 in decimal, right? Any other questions? All good? Okay, so last time we stopped around here. We went a little bit fast, a little bit further, but I wanted to recap from here. So essentially, at some point, right, the trap function, which like this is the call chain, hardware lands us on the interrupt descriptor table entry, which is x64. Then we like call the, like inside this interrupt descriptor table, there will be a pointer to the interrupt handler for this specific entry, which is called vector 64 in x86. Then we will go to a single generic label, all traps, which pushes all the registers on the stack. So to make sure that we save them before like jumping into C. We then jump to C function, which is called trap, which processes the interrupt because it's convenient to have to write in C versus to write in assembly, right? And then eventually trap, when it looks at the interrupt number, says, okay, this is really a syscall, lands on a syscall function. And inside the syscall function, the convention is that the user will pass a system call number inside the EAX register. And depending on this number, there will be a table. Essentially, x86 creates a table of system calls, and this is the entire table. The table is an array of function pointers, right? So you can do that in C. I don't know if you realize that, but I mean, you probably are, right? You just say, look, for the sysfork number entry, the sysfork is the function, right? So do you understand how this table is organized? It's just an array. And imagine there is a entry number sysfork, right? This is the number, whatever it is, probably it's number 0. And inside there will be a function pointer, which really leads us to the function sysfork, right? And so we can invoke it. Like taking an entry from the array, using it as a function pointer, and just invoke it, and it will return the result, right? Which we place in EAX and we'll return it to the user, right? That's again kind of an interrupt calling convention, right? The EAX is the number of the system call, not interrupt, sorry, system call calling convention, and then we'll return result in EAX. It makes sense, kind of, right? So, and where we stopped last time was the question of how users actually invoke interrupts, right? After all, it would be just kind of weird to write in your code pieces of assembly kind of saying, which says, okay, int syscall, which this one is x40, right? And you say, I will push some interrupt number on a stack, and then I will push some arguments, right? And naturally, you would say, I mean, you're familiar with compiler intrinsics, right? So this is kind of the same idea, just that it's not a compiler intrinsic, but we generate a function, kind of like if it's sysexec is probably not the best example because the function arguments are slightly convoluted, right? So it has a pointer to the array which says it's the name of a program in it, and then a pointer to array of arrays, right? So essentially, and each of this array is kind of an argument, right? So for example, WC minus L, this is the argument to WC, it's minus L, right? So minus L will be passed here, and instead of this init, exec will get argument WC, right? And it's okay, right? But the question is like, how can we generate these functions? You say, look, okay, hold on, I know what to do. I will use essentially a header file in which I will let the compiler know which arguments exec takes. So this is the name itself in it, and this is this pointer to array of arrays. That's how you write it in C with this double stars, right? So this will be array of arrays, and the last element will be 0. That's okay. And then the compiler knows how to generate system call invocation, right? So by looking at this definition, right, it will know that it will generate call to the right function, right? And it requires 3 arguments, right? So I'm jumping here between right and exec, which is yet another weird thing here, which I'm doing. So this is argument number 1. This is the file descriptor number 1. This is pointer to the buffer, and this is length of the buffer, right? Okay, so we kind of understand, right? And as I told you, that different versions of GCC might generate like slightly different code, but this the call to the function, which is like right, is not yet implemented because it's still just a header, right? So, and somewhere we need to implement this code, right? Kind of provide this compiler intrinsic here, right? But we will provide it ourselves because GCC doesn't know anything about it, and we don't know to bug GCC developers to just add support for x86 kernel, right? So what we're going to do instead is we'll use a C macro, which is also a very convenient mechanism, which says, okay, look, the macro itself will take the name of a function and will define a global label. Why is it global? So the compiler can resolve it, right? So when we generated call to write, remember linking and loading, this symbol has to be visible. That's why essentially we have to say, look, there's a global name, globally visible name, right? And inside that name, we'll provide a simple assembly sequence. We will put the system call number inside EAX, and we'll invoke the interrupt, right? And that's enough, because at this point you drop into the kernel, go through the interrupt descriptor table, and the kernel kicks in, starting from this vector 64, right, and so on. But the user did its job. So now the question is, how do we pass the arguments? Where are the arguments to the interrupt, right? Let me stop here for a sec. Just again, stop for questions. Did you guys get the point of using this macros? So essentially each macro, we use it once for each system call, right? Expands. And the macro itself doesn't really know the arguments at all, right? It just says, okay, this is the assembly sequence, that's all. So how does it really work? It actually works because the compiler already generated the call side invocation, and it already pushed the arguments to the system call on the stack, right? And we just kind of like say, okay, we will execute on the same stack. We don't even change it. We'll just use this EAX register to put the system call argument in the EAX. Why EAX is a good choice? Who can tell me? What good properties EAX has compared to other registers?
It's the return.
The return value, right? But we are not really returning. So it's a good idea to return something from the interrupt inside the EAX register,
it's
right?
callie saved.
Exactly. So Shane on chat, and you're correct. It's callie saved. So if the caller wants this value, no, it's caller. It's caller saved register. That's why we can override it. So Shane, you're wrong. Actually, it's not callie. It's the other way. But I hope that you guys, both of you, I hope that you meant the same thing. The thing is that we can freely override this register with any number. Because if the caller wants this value back, whatever the old value back, it has to save it anyway, right? So that's why we could have picked any caller saved register, right? Okay. So is that clear? Or is it still a little cryptic how it works? I will ask you to build a new system call in x86. So listen carefully, although it's very simple, to be honest. It just for the very first time, it's hard to connect the dots. But I bet like it's not that hard.
Professor?
Yeah, go ahead.
So pushing like the arguments onto the stack for the system calls, is this only how XP6 works, or is this for like all general OSs? It's handled in this manner.
Yeah, so that's a good question. So I think most operating systems will push, in general, x86 actually, it's a good model of how a real operating system works. You can find, and I don't remember exactly how Linux works, but I'm pretty sure that they will push arguments on the stack as well, because you can pass several arguments in registers, right? You can come up with a calling convention which says, okay, for the system call, I will, again, depending on the architecture, right? And it kind of makes sense to, okay, hold on. It kind of makes sense to mimic the calling convention of the underlying architecture, because it's easier for the compiler to generate this call site, right? If you want to implement a different calling convention for a system call, you can move those values from stack to registers, but you already put them on a stack. So kind of moving them again doesn't save you anything. It just adds additional hassle, right? So for example, if x86 64-bit calling convention allows you to pass several arguments in registers, this is how the system call convention will look like as well. Just because then the arguments will be in registers ESI, EDI, if I remember correctly, right? And so on, right? Because then the compiler already puts the arguments in those registers. Then you simply, in this intrinsic which we implement, you just move something inside the EX register because it's a caller safe register, and the caller expects to return a value, get a value back, get a return value in this register. So it's okay to override it with a syscall number and just go forward, right? So it's kind of convenient. Do you get this point?
Yes, I see. That makes sense. Thank you, Professor.
Okay. Yeah. Any other questions? Okay, let's move forward. So, okay, this is where we stopped for real last time, but I was rushing a little bit, so because I wanted to finish, but I ran out of time anyway. So the question is, where are the system call arguments? Who can tell me quickly?
The user stack.
The user stack, exactly. And Dominic has it as well. And this is amazing because you have to clearly understand it, that there are two stacks, one of the user stack, and the user pushed those arguments here on this user stack. And then we went through an interrupt into X40, right? Landed on like, while going through the IDT, we actually changed the stack. Who can quickly tell me why did we change the stack?
We don't trust the stack pointer.
We don't trust the user stack pointer because it can point anywhere to any sorts of garbage, like, or even into the kernel itself, so which would allow user to accidentally override the kernel, right? Typically, kernel code is mapped read-only, and this is how we map it to x86 as well, right? So you can't really override kernel code, but you know, like there are many attacks which don't require you to override the code. There are data-only attacks which actually just, in many cases, are Turing complete, calling like only legit functions in the kernel. So you can, like, it's a little bit tricky. So even I advise you to read those papers on data-oriented programming. But essentially, overriding the heap or stack is good enough to start, you know, to start abusing the kernel, right? There is also return-oriented programming as well. But data-oriented programming is even more fancier. So it just doesn't even need to return. It actually uses only allowed calls and returns, right? So it doesn't abuse the control flow graph at all. And this is amazing, right? So, but let's get back to this. So how inside the kernel, of course, and this is an example of a sys, right? So what kind of checks we have to do? Because this is how the user calls the syscall, right? So right, it passes a number, a pointer to a buffer, and a length of a buffer. So what do we have to check to make sure that the kernel can start running and executing on this system call? So how does the user can abuse the kernel by passing some rogue values in those arguments?
The n can be like arbitrarily large so that it can write like a lot of data.
Correct, right? So n can be arbitrarily large. What else? The buffer can point to any address Dominic says on a stack. Correct. What else?
The file I can write to some, the FD should be valid. Okay.
Yeah, so file descriptor should be valid. And this is exactly, and I'm just using syswrite as an illustration, but the kernel has to do that for every system call, right? So this is the code of the syswrite. So it does those three checks. First, it checks that the file descriptor is a valid thing. The n is actually, so argument number 2, is a valid integer. We'll check this in a second, right? What it means, and then it checks that the buffer p is and of size potentially n is within the range of the address space of the kernel. So let's go step by step. It's a little bit like I want to spend some time, but this is how the real kernel will do it as well. So it has to validate the arguments, right? And if one of those check passes, if one of those checks doesn't pass, you return -1 to the user. And however, if everything is correct at this point, you say, look, I can invoke an internal function of a kernel which does a file write, which will use this file descriptor, will use the pointer to a buffer, and there will be a length of this pointer, right? And we know it by this point, by then we will know that the buffer is pointing to the correct user memory, and the size is also of this buffer is also within the range of user memory. So let's double check. Let's go step by step and see how it works, right? So the 3 checks. So check number 1. So the first check is that the kernel itself doesn't even know that n is a valid integer, right? It's a little bit unusual, right? You say like, how can it be? Because maybe the user is malicious and it points to some like it points n because maybe the stack itself is crossing the boundary of a page, right? And n is kind of like on half of that page, right? We need to make sure that this integer is within the address space of the process, right? So we say, okay, where is this nth argument located, right? So it's located on a stack, right? And okay, this is the layout of the user stack, right? So the top of the user stack is pointed by, or the bottom of the user stack is pointed by the ESP register, right? There will be a return address. Remember, we did this call write function, right? And the return address was pushed on the stack. However, the intrinsic which we generated doesn't maintain the stack frame, so we didn't do anything with the stack. We just loaded EAX, right? And so we say, look, we have to skip this 4 bytes for this return address, and then we'll say like each argument is 4 byte long, right? So we add 4 multiplied by n, and we check the 4th argument, right? In our case, we're checking argument number 0, right? So it will be this value on the user stack. And what do we have to check for this argument? We have to essentially, we use this function which is called fetch integer. It's called fetch an integer from the user address space because we don't really trust. Maybe the user address space ends at exactly half of that integer, or maybe 2/3 of that integer. So maybe not entire integer fits into the user address space. Maybe user tries to fool us because if it doesn't fit into the user address space, the kernel will try to access it and will exit with a page fault, right? And it will be very confused because it says, okay, why did I page fault? I'm not supposed to page fault inside the kernel. So, which will probably panic the kernel, right? So this fetch integer function, which is here, so this is I have slide by slide here. So the fetch integer function checks for the following things, right? So remember, we pass the address. This is the adder. we check that this error is within the range of the user address space. So what are those checks? What is this proc size value? So the proc size value is essentially the size of the user address space, right? Because user address space contains the following parts. So, and we will take a look at it today, but let me just believe me for now. So there is a text section of the process. There's the data section of the process. We'll create a guard page to prevent like stack overflows or to detect them early. There is the stack page, and there will be dynamically growing heap. And every time we increase the heap, we grow the proc size variable inside the kernel, right? To know the number at which the user portion of the address space end. And what we're trying to check is that we say, look, the integer which we're looking for has to be here. Maybe it's here. Maybe user tries to fool us, right? And we will eventually override or read from the text section of a process. It's okay, like there will be some number, we'll just check it, we'll trust the number. But what we have to ensure that when we read, the read doesn't exit with a page fault. So we check that it was in the range of the user address space, right? So that's why we say, look, we're looking for an integer, we check that the address is not larger than the size, and the address plus 4 is not larger than the size itself, right? That's correct. Why do we have to check it twice? Why can't we just check address plus 4? Because after all, we kind of believe that if this is the proc size, the entire integer has to be less than proc size, right? So why one check is not enough? Tricky question.
Error can be at the end of proc size, right?
It can be at the end of proc size, like this?
Yeah. As in like, so like it can be like from proc size to the next byte or something.
Right.
Like
so, but supposedly this check should handle it, right? As long as this end, the end of the integer should be less than proc size, right?
Yeah.
So, but why do we do 2 checks? So I'm kind of claiming that this check, error plus 4 greater than proc size, is not alone because of a possible overflow. Exactly, right? Because the user might be so bad that it will say, look, this is the very end of the address space, which has all Fs, right? And for example, it will point over here, then this part of the integer, right? Because it's size plus 4, will be byte number 2, for example, right? It definitely less than, it's smaller than proc size, but the kernel will be confused and will try to fetch it from here, right? And who knows what happened? Maybe it will be a complete overflow. Maybe it will be just some kind of machine exception, right? I don't even know how the hardware will handle it, but we try to prevent it, right? And that's why we check for both, right? That's a tiny nuance, right? But you have to understand that every line of the kernel actually makes sense, right? There are bugs in x86, but they are rare. Okay, that's good, right? And if we say, look, we pass the checks, now we can actually read the number. So this is a unified function which fetches an integer from the user, right? We now know that we can trust this number. It's really something what is within the user part of the address space. We don't really know whether it's within the stack or within the heap. We don't really care if user tries to abuse us a little bit. It still will interpret it as a number, and then we will do whatever user wants, but user can pass any number anyway, right? Okay, now we say, look, let's read this number and return it into this parameter, right? So with effectively what we did here is we actually looked at something like argint. So we read this n. So we're looking at argument number 2, right? I promised to like check the argfd, but you can look it up yourself. So I don't know if I have a slide for it, but essentially we just checked that n is a valid number, we can read n from the user address space without crashing. Now we're going to check whether the buffer is buffer plus n is smaller than the size of the user address space. So it's essentially the same logic. So we say, first of all, let's we don't even trust this pointer to the buffer. It can be, again, the same kind of logic. It can be at the very end of the address space, can cause an overflow, can crush it in any possible, can crush us in any possible way. That's why we will be using our save arg_in function, which will access this pointer, this argument number n, right? Then we got the I from it, right? It's a pointer to the buffer. We do the same check for the pointer to the buffer, checking that the beginning of the buffer is within the address space and the size which we passed. So the end of the buffer, meaning that the beginning of the buffer plus size, is also within the range of the process address space. If we fail, we just return -1 here right away. If we don't fail, we say, look, okay, we can trust this buffer. It is really within the address space of a user, right? Within the user part of the address space, right? So it's totally fine to say that this argument is legit, right? Okay, so, and just to make sure that we understand that how, I just wanted to make sure that we understand how arg, how this arg file descriptor work, but you probably can already guess it, right? So you say, let me just quickly grab arg fd, probably it's something like this. This is the check for the valid file descriptor, right? So what happens here is, again, we check first that we can trust this integer. Then we say if it's less than 0, go away. If it's greater than the size of a file descriptor table, we also don't pass the check. And finally, we say that, okay, that's really like there is a file and it's not 0 at this location. So it's at this point, we can essentially convert the file descriptor into the file pointer, which will return right here, right? Let me stop here again. So did you guys get the logic of those checks? So let me unroll here slightly. Somewhere over here, that's a good point. So this is what we were checking. So essentially, or somewhere over here even, for the right, sys_right function. All good? So in your homework, when you're gonna add a new system call to the kernel, make sure that you use those checks. And I will be asking you about those checks later in the class as well. But for now, everyone is clear. Everyone is happy about system calls as well. So because we're done with system calls. And we will, well, actually, I wanted to do a tiny detour. So we talked earlier in the class about like printing on the console, right? And at some point, it's it's a little bit magical that some strings show up on the console. So we have this cprintf function, right? Which essentially takes a string, does some formatting on this string similar to printf. So in this example, we put a CPU number instead of this D directive, which tells us, okay, that we want to print number really here in place of this %d, right? So this printf function, right? So what it does, it can actually, if you look at the user level part of this function, so essentially the one which user can invoke, right? So, but actually looking at the kernel part for whatever reason here. But the idea is that, so we do the formatting. So really, if you want to implement this printf, so you say, look, is this character is a %, right? If it's %, then, we get ready to, if it's not %, then we just simply put something on the console with a const put c function, right? So this is the function which puts a character on a console. If, however, not, then we will do the formatting. So like, for example, this is example for a string, right? So you say, look, if someone passes s, it means that we will try to get an argument which user passes, and we will essentially, like it's a string which user wants to print here. And so we'll take this tiny loop and we'll print it on the screen character by character, the string. So for example, if you say something like cprintf, and I will say something like %string, and then world, and then we say here hello, right? Sorry. Then essentially what we'll be doing in place of this s, we'll be printing hello first here, right? Do they have a case for an SK character? They probably do. Like I can quickly look it up for you, but I mean, x86 is a decent thing. Cprint f minus r, and is there escape? So this is their escape case. So how does it work here? So you have to put, if you want to print this character on a string, then you have to probably put double percents, right? But again, so you can take a look at the source code yourself, right? But the idea here is that at some point, so for example, this function which puts a character on a string, right? It uses essentially another function which is called uart_put character, right? And this uart_put character essentially says, okay, I know the serial line protocol, right? And I will be essentially doing a little bit of a delay here, getting the console ready, right? And then essentially putting something on a serial line by essentially outputting something in a serial port COM1, right? So again, so why this is useful? It's useful because you can say, look, I can actually read through the entire operating system kernel, and I can see like every time, like even when something is happening at user level, right? So for example, how do we think a user level printf function? And I can ask you, okay, so if a user level code has printf, which says hello, can you explain me what actually happens inside this printf? I would like you to be able to reason about it. So you say, look, okay, I get it. So I don't really know how printf works, but I probably can think about it. And I can edit something here like user.h, right? So there will be a function printf, right? Those functions will be implemented into this ulib.c file. I can go there, and you're totally fine to use any like cross-referencing tool to help you, right? So where is it? Oh, it's not here. Then grep for it. Yeah, minus. There will be a lot of printfs. So how can we quickly look? Console, this is a kernel level function. Okay, this is the implementation of a user level printf. It's very similar to the kernel level printf, right? It will have, again, the same formatting logic, but what do you think? How do you think this putc will be implemented? Essentially, you know, you run it inside the user level. You link again the library, which implements printf. It's very similar to how you link against libc, which implements printf on Linux kernel. What do you think is inside this putc function? In the end, the goal is to
I think a write system call.
Exactly. So there will be a write system call, right? So if we want to see what's inside this putc, again, God, I was thinking I will land on it, but inside the putc, you will find a write system call. Oh, it was there. And the write system call will just put one character. So the pointer to the buffer is the character itself. The size of the buffer is is 1, right? And it's again, it's this beauty of IO redirection. You're printing out into the file descriptor, right? And normally this file descriptor will be connected to the serial line, right? But in reality, it might not be, right? It might be redirected into a file. And if we go into the kernel, and we know how write works because we just looked at it, and we see for something like file write, and we find it inside the kernel, this function which essentially writes into a file, it first will check whether it's something special. It will actually I was under impression that actually write I, okay, maybe it's too early to look into this. I was hoping that there will be immediately a check. Right, I will be a check for whether it goes on a console or not. And let me maybe quickly see if this is the case. Maybe I was wrong altogether. That's the definition of the time. So this is it. This is do it again. Okay, here's this check which I was looking for. So write I is a function which writes into an inode normally, but here it also can check for whether it's the inode is of type device, right? And the console will have this device type, right? And all these devices will be kept in this special table, which is this def SW table, right? And they will implement a write. Like we can see how this table is initialized, def SW minus RR. So for the console, there will be essentially, when we initialize the console here, right, we essentially will initialize the entry in this table, the entry for the console, to have a specific write and specific read function. And the specific write function is this one, console write function, right? And essentially what it will be doing, it will acquire a log to make sure that only one process can write to a console at a time, right? And it will put a character on a console, this console put C. And this is exactly what we just saw on the slide. So this function, which is console put C, will be using this UART put C function, and UART put C function is right here. It will actually put a character on a serial line. Okay, so maybe this detour was a little bit confusing, but what I meant to say here is the following, right? Let me just recap everything for you here. So when you have a user level printf function, right, which prints like hello world, it's a library function which is implemented inside user, right? Inside user library. What it will do internally, it will do the formatting in a loop, right? And it will eventually invoke a write fd system call by putting a address of the specific character and a buffer1. This will land you in a kernel with an interrupt, right? Because remember how write works. It's just the compiler generates a call site invocation. Then internally we use this int x40, right? This write lands on, remember, the full pass through the kernel, vector 64, then all traps, right? Then trap, then syscall. This will land us on syswrite. This syswrite itself will check all the arguments and will do a file write, right? The file write function itself will do, let me just detour here, will, like, or not detour, but go up, will do something like write I function. Inside write I, we check for whether this is a device type. The inode is of device type, and we'll land on this def SW table when we call the write function, and this write function will land us on the console write, right? And this console write will internally will use this console put C function, and then we'll use UART put C function, right? This is what I wanted you to understand essentially, that first of all, like if I ask you a question, what happens when you invoke a printf hello world system call? You can actually reason about now, and your reasoning will become more complete, because like what's missing now? The only parts which are missing, let me change the color here, are the parts which talk about this low level details of the file system, like write I, right? But everything else, like file write and write R, right? File write and write I are kind of two functions which are a little bit vague at this point, but everything else is there. So you know how the printf works, right? It just explained it, because how does the formatting, you know how write is implemented with a file descriptor, how it goes into the kernel. So this is where you crossed from ring 3 into ring 0, right? And after that, everything is inside ring 0, right? So pass to the kernel, then pass to the kernel source code to essentially invoke a specific console function, right? Is if I stop here, and if I, okay, let me stop here for questions, but that's the whole point. I mean, I wanted you to understand what happens when you do a system call, when you like, I might ask you like, what happens when this instruction executes? And you have to explain me, like you have to be able to reason about the entire kernel and be able to tell me, okay, this is the chain of functions and this is how the character gets on the screen. Okay, did I confuse you too much? Too fast? File write determines device. How? So this file write, that's a good question. So I know that, you know, Andrew was not confused completely, which is great. So this is the idea, look. This inode, which is associated with the file descriptor, which we were using, right? So we're using this generic write I function, and this inode, when we open it, right? So when you open a file, and we will talk a little bit about when we reach the file systems, right? But it's totally, it's a good. When we open a file, essentially at this point, we can look up these two magical numbers, which essentially, I mean, this is the major and a minor number for the device, right? And the major number determines the entry in this device table, right? That's how we get to these numbers. Because we might have multiple serial lines in the system, right? Depending on how we open the console, and we'll take a look at it. So, but essentially when we do init, so the very first process, right? This one. This is the very first process which starts on the system. It will create a special file. It will check if this file already exists in the file system. And if it's the very first time we boot on x86 file system, it will use this mk node system call, which says, okay, I will create a file, but it's not really a file. It's a device file, right? So it's like typically those are the files which are sitting inside dev, something like console, whatever there is under dev. Let me show you here. L dev on my system is this, right? So all these files are not really files; they are devices, right? And the like I have this dev console as well, right? And it will have a major number, not minor numbers. I think those are the two, which are created. And x86 does the same with this mk node system calls, right? It's a way to create a file which is backed up by a device, right? And there must be a convention. So when you open a file, you must understand that the kernel will treat it specially, so that this the console initialization code will initialize the console in such a manner that it will say, okay, I will create an entry in this dev SW table, right, which will correspond to this major and minor number. So specifically major number here. Does it help, Andrew? Yeah, okay, good. But again, the beauty of it, and this is kind of where we get to this beauty of x86, where we say, look, I can read the entire kernel, and it's not like, it will not kill you. If you try to read Linux, you will be on your knees. So it's very hard. So without years of experience, but reading x86 source code is totally visible. I do it without even cross-reference, just grabbing through the source tree, right? Okay, so any other questions about system calls? And we'll move on to the next lecture. I'll start moving meanwhile. Okay, so our second topic today is exec. So again, remember what we've done so far. We learned how to create the kernel part of the address space, right? So this part, so essentially this was the magical function, set up KUVM, set up KVM, right? So set up kernel virtual memory, right? That's the one which maps all this 4 regions to whatever, to the bottom of the physical memory plus the IO region, right? And the goal of today is essentially learn how the x86 kernel create processes with the exact system call, right? And then what we will do, we will understand how x86 creates the very first process, and it will be somewhere over here, right? User init. And then we'll kind of understand how the kernel boots and starts running shell, right? But today is essentially our goal. If we already understand how to build this part, today our goal is to understand how we can create this part of the address space, right? The user part of the address space, right? So, and we know how to create it. We know that it's done with the exact system call. After all, we did the homework on that, right? So we did shell. We understand very well how the interface of the operating system. The question is like, what needs to be done mechanically here, right? So if you were to write this code, what is there you have to write to make sure that it works, right? Okay, so if I ask you a question, so how does kernel creates a new process, right? You quickly will answer me, like it's because it's an exact system call. It takes name of a program, right? And takes a pointer to the array of arrays which represent arguments, right? Remember that each argument is a string, right? That's the convention in Unix operating system. And last element of this array is actually 0. By convention, the first element is the name of the program itself, so it will be ls, right? Well, not new line, it has to be 0 here. And then whatever the other arguments are, maybe it's -l, will be this element of the array, right? Agree with this? So, okay, so let's talk a little bit about the memory layout of the process, right? So what do we need to create? We obviously, this being, what is it we're creating here? Bin ls. Bin ls is an ELF file, which is sitting in a file system, right? So when we load it in memory, first we want to understand the ELF file format, right? Similar to how you did it in the homework, in the previous homework. We want to load the text section of a program in memory, and on x86 we load an address 0 because we force all the programs to be linked to run at address 0, right? That's totally fine. We could have chosen a different address, but 0 is not worse than anything else. Then we will load the data section, right? Then we'll set up one page, and it will be a guard page, which will be preventing the stack from overflowing. Essentially, we'll create the stack page right above the guard. And if the stack happens to spill into the guard page, this page will not be mapped as user accessible, which means it will cause a page fault, right? Or some kind of a protection violation, which will catch in a kernel and will terminate the program, right? That's kind of useful. And then there will be a program heap. This is like at the beginning, when we start the program, the address space, so proc as z will be ending right here. But later on, if the program does malloc and malloc uses sbrk system call, it will grow its address space, adding more pages here, essentially growing its heap, right? Okay, so at a high level, the overview of what we want to do is clear, right? So we want to load program from disk. We'll create a user stack. Then we will set up the instruction pointer to the entry, which we get from the L file, and then we can run, right? Agree with that? After that, the user process runs. This is the high-level overview of the exact system call, right? Do you agree that this is what we want? We don't need anything else. Do you agree? Where does the user program page table comes from? It is constructed by the kernel. Is it a copy of the kernel page table? Great, you're right. So this entire address space needs a new page table. So even before doing any of those manipulations which I just described, we have to create a new page table, right, for the user process. And moreover, this new page table has to contain this yellow part, right? Because we always want the kernel to be mapped in the same page table, so the user can do int ox40 and land on the system call handler, right? Agree with that? So the very first thing which we need to do is we want to construct a new page table. I totally agree with you, Dominic. That's a great observation. Any other observations or questions? So we're learning how to create new processes by looking at the implementation of the exact system call, right? So there is a little bit of this chicken and egg program. I did not explain you how the very first process is created. I will explain it later. So imagine this very first process is already created, right? But imagine it invokes exec, which means that it will reload its own address space, and it can invoke fork to clone itself, right? So it can clone itself with fork and then use exec to reload its own address space. I'm not going to cover fork, so you will have to read about it on your own. But exec is a little bit more involved because it's not just simply copying memory, it actually loads something from disk. But again, let's do it step by step. Like again, a little bit of an overview, right? So inside exec, if you were writing it, if I would assign it as a homework, you would do something like this. You would read process binary from disk, right? Because you want to get this L file after all, right? So in order to locate the L file on disk or this specific file on disk, there is a file system function which is called name_i. And we will, when we look into file systems, we will understand how this name_i works. But at a high level, it converts a symbolic name, something like /bin/ls, into an inode. I stands for inode, right? So it takes a string and converts it into an inode. After that, you can use this read_i and write_i functions to read and write this inode from disk, right? And again, when we get to file systems, everything will become clear, right? But just trust me that name_i is part of a file system. Read_i and write_i are also part of the file system, right? So this read_i, for example, specifically reads the inode file data from disk into memory, right? But as Dominic mentioned, to read the file in memory, we need to construct the process address space because we need to read it into somewhere, into some pages in memory, right? And this is a new page table for this new address space, which exec is currently creating, right? You could have imagined a different logic. You could say, look, maybe I can just reuse the page table because something was already running when exec started executing, right? So why do you think it's a bad idea? Why do you have to construct a new one?
The memory footprint will be less. We might have mapped pages that are used by the old process that are no longer required.
We can probably garbage collect them somehow, like reclaim them back. But there is like one like silly reason which kind of like breaks this idea of reusing the address space. And the silly reason is that exec might fail halfway. Maybe we're gonna run out of memory, right? So because maybe the L file is so giant that it may be even larger than 2 gigabytes, or maybe it's just large and we already have so many processes that by the time we loaded everything in memory, we want to create a page for the stack, and allocator tells us, okay, you ran out of memory. At this point, we say, look, like the only sane logic is to return an error from exec, right? But if we destroy the old address space, there is no place to return the error, right? Because it's already gone. That's why it's much easier to essentially say, look, hold on, guys, we'll just construct a completely new address space. And if everything will go through, right, then we'll just simply say, okay, we got it, right? We'll just, at this point, we'll delete the old address space, but and we'll return and we'll start running inside the new. Is this argument clear to you guys? Is it clear? Why we're building a new one? Yeah, okay, good. Okay, so let's start. So essentially, we know how to read the kernel source code. I skipped a couple of lines, but it's okay. So we are inside the exact system calls, essentially all the same logic, like vector 64, yada, yada, yada. At some point, you land on the entry inside the syscall table, which essentially lands you on sysexec. You validate the arguments already, and you're inside the exact function. So the very first thing which we do is we say, look, this is the pass, which is the pass to the new process we're creating, right? We pass it inside this name_i function. Name_i function, if everything is good, gives us an inode back. Inode is the abstraction which allows you to read the file from disk, right? Okay, so far so good. So we say, okay, let's check if it's an L file altogether. Maybe user tries to open some text file and tries to fool us into something, right? So we say, look, let's read a little bit of this inode. We'll just read in a temporary variable, which represent the elf header, and we only read the size of elf header entry. If we didn't read enough, if the file is too small, we just go to some error, right? If we read something from a file, but it doesn't have a special elf magic, again, user tries to open not an elf file, so we again exit with some error code, right? Okay. Now, the next step, we want to create this process address space. We want to create a new page table. It's a two-step process. Remember, I told you that every process has a kernel part of the address space mapped in the upper half of the address space, and the lower part will be user, right? So let's go it step by step. Remember, this is the logic, right? The kernel is always mapped, despite the fact that we might run different processes. This is a pink one and this is the green one, which will have different physical pages backing up their virtual memory, right? The kernel part will be always the same, right? x86 takes a shortcut and it maps it in a brutal way. It maps it always, like instead of like doing some kind of a sharing of those pages between processes, it just always maps it brutally with a well-known function, which we already covered before. Remember this function? It's called this setup kvm. So setup kvm, remember it does this, remember this map of kernel regions, right? And what it returns a page table. It's a page table which contains nothing for the user part of the address space, right? But will contain those four regions, this IO region, the kernel read-only memory, the kernel read-write memory, right? And the IO region at the very top, right? This is the page table which the setup kvm returns, right? And we do remember how this function works. I just like to refresh your memory. This is how we looked at it before. So the setup kvm allocates the root of the page table and then essentially goes through all entries of the kernel map, mapping those regions into the page table, right? Remember this? Memory fails you. Okay, I understand, right? But at a high level, you can trust me. Okay, yeah, this is what we did, right? So this is the four regions which we were talking about. This is like 1, 2, 3, and 4 region, right? And this is where we map this. And this part is still empty because this function doesn't know anything about it, because this will be coming from disk, right? This is what we want to do. We want to do exec and read it from disk, right? Okay, so we refreshed our memory here. So it essentially like goes page by page, right? Now the second part, we want to map the user part of the address space. And this is like kind of the essence of today's lecture, right? So how will we do this? Again, it's an iterative process, right? Our goal is to bring the kernel text and kernel data from disk into memory, right? So, and it can be combined with reading those sections from memory, sure, right? So essentially, what we're going to be doing is we will create a loop And on each step of this loop, we'll be allocating user level pages, right? Essentially a page starting from address 0, then a page starting at address 4 kilobytes, then the next page, right? And every time we allocate a page, we read something from disk, right? So like first of all, we'll read a text section, right? We say, look, text section spawns from 0 to maybe like, I don't know, 8,500 bytes, for example. So we will allocate 3 pages and we'll essentially load them from disk from the text section here. Then we say, like, what is the next section? There will be maybe a data section, right? Although I think x86 bundles everything together. So to simplify the loading, right? Again, right? So let's take a look at it, right? But it kind of, at a high level, it's kind of clear, right? So you say, look, I will allocate it page by page. Some pages will be for process text, some will be from process data, and every time I will allocate a page, I will load it from disk, right? This is what you want, essentially, after all. This part was already created by a setup kernel virtual memory function, right? And this part you will be filling in inside the exact system call, right? Agree with this? Okay, let's take a look at how it works. It's essentially same syscall, same exec, just slightly down from where we looked before. The size of the address space is still 0. It starts from 0. We'll say, okay, I'll be looping for each entry in the ELF program header table, right? Right. That's how we would do that. That's how you did your ELF loading, right? We don't know how many entries are there, but we're going to loop, right? And every time we will be just reading one entry from the program header table, right, from the ELF file. And so this is what we're doing here. So we will, that's just a reminder, right? The ELF header has a program header table. There will be a pointer like this, right? And the program header table will contain pointers to the text, read-only data, writable data, BSS, stuff like that, right? So we know the deal, we know the logic here. So we say, okay, I'll get an offset, which I read from the ELF program header table, right? That's how I start. And I read an entry, which is the size of one entry in the program header table, right? If something goes wrong, I fail, again, go to bed. If it doesn't fail, right, what I will do is I will allocate enough pages in user part of the address space to essentially load this entry from disk. So essentially, I read ph, right? Ph will have a virtual address where this section has to go, and it will have its size, right? So essentially, this alloc UVM will take the page table, which we already created, will take the current size of the address space, and we'll essentially say, okay, we'll take a virtual address plus the size. Let's take a look inside how it works, right? So I have I highlight those arguments one by one. But before doing that, let's say, okay, if the memory allocation went through and we get the size back, right, and it's not 0, right, we will essentially use the second function, which will load this data from disk. Essentially, 2 functions. One allocates memory, one loads everything from disk, right? So this one, load UVM, will read the disk and will load it into freshly allocated chunk of user address space, which this alloc UVM returned, right? Is this high-level idea clear to you again? Okay, thank you, Dominic. Otherwise, I would be lost because I don't see anyone. Okay, this is how it works, right? So alloc UVM, allocate this part, those pages, load UVM, load the pages with data from the ELF file, from disk, right? Seems okay, seems good enough. Let's take a closer look at this alloc UVM function, which allocates the memory, right? So essentially, this is where it gets a little bit tricky. So those pages which we'll be mapping here, right? We'll map them at address 0, right? For example, or next to 0, right? But they will be located somewhere in the range of available physical memory, right? And remember, we mapped all these pages, right, with a 2 GB shift, right? So they will be sitting here, right? And they're on a list of our free pages. Remember, our allocator eventually ended up with taking all the available physical memory, right, from the end of the kernel to fizstop. This is the fizstop constant, right? And all of these pages are sitting on the free list of the memory allocator, right? And this is effectively what we will be doing, right? So if the user tries to fool us and says, okay, this new size is larger than 2 gigabytes, and just return. User tries to do something weird. It tries to override the kernel, right? If, however, we pass this check, we round up the old size, because old size is already mapped, right, to the next available page, right? And then we essentially will say, look, I will use a kernel memory allocator to allocate a page, right? This is what we were doing before. Do you remember where this page is coming from? It comes from this linked list, right? We talked about it. Do you still remember? Right? Great. This is the allocator, right? We set the page with zeros just to make sure that it's cleanly initialized. And then we'll use the same function which we used before. Remember, map pages. It takes the virtual address, it takes the physical address of a page, right? It takes the size of the region. In this case, we just map one page to page size region, right? It takes the page table here as an argument and takes the flags. So we say it's user writable and user accessible, right? We used this function before. So this will walk the page table, allocate the page table entries if needed, and will essentially provide the mapping, right? So the allocator returns us the memory address. Here we use this macro, which converts this virtual address to a physical address, right? Because this is physical and this is virtual, right? Okay. So I guess I go one by one. Again, I remind you what map pages is doing. So essentially it was walking the page table, finding this entry, and essentially updating this entry with a valid flag. Internally, what it does walk page table directory, right? Returns a PTE, and then we will, those flags which we passed here, we'll just update the entry with those flags. Very similar to how you're doing it in your homework, in the very last homework, right? And again, like if you forgot the map pages walk page table directory, I advise you to quickly look at it, right? So it's reasonably easy, right? Okay, and then we're going to be alloc-UVM. We're going to be going in a loop, right? So we started from address A, we increment A by page size, and we'll keep going until A is smaller than the new size, right? We'll keep mapping page one by one. So reasonably simple, right? So essentially page by page by page, right? Okay, cool. So now the second function, since we already have the memory there, our second goal is to load the sections from disk, right? After all, that's what we want to do. So as I said before, the high-level outline here is the following. Use the name_i function we already did it, right? So we already have an inode. So essentially we're right here. So load program memory. So read the data from the inode into that memory. That's easy. So this is this load UVM function, still the same page table, virtual address of where we want to load it from file, right? This is the virtual address where the text section, for example, or the entry in the program header table has to be loaded, right? The offset was in the file inode itself, and the size of the entry in the program header table. Again, very similar to your homework. So essentially, we're implementing this error here, right? And maybe there is just one section. Maybe we compiled and linked the kernel, the user process in such a manner that everything just is bundled together. And I don't really remember how x86 does it. Okay, so load UVM. So this is a little bit tricky. So this we probably should start next time. So this function, what it will do, it will load in the end, what will happen is that we're going to be reading from a file which is represented by the inode. into the virtual address, which represent the address of the process, right? I will explain it next time. You might say, okay, why can't we just use this? Like, let me just give you a hint why it's hard. Why can't we just read? Imagine we're like pH, this virtual address, for example, is 0 for the sake of it, right? Because imagine the user tries to load something from disk into this 0 address, right? You might ask yourself a question, why don't we just simply use address 0 here, right? Or like the address which the user passes, this error, right? Do you see the problem with this? It's a little hard to see actually. Verification, no.
We should change the page table register. Like we should change the page table entry thing, but that can be done, right?
The problem is that what we're doing is that we are currently running, our CR3 is pointing to the old page table, right? Which has something at this address 0. And we're loading into the address space, which essentially is controlled by a different page table, by a new page table, right? That's why essentially we have to convert between the addresses between the old and a new one. And I will come back next time and I will explain how it's done. I will probably start with a good figure, which talks about what these two page tables are and how they are positioned in memory, right? So let me stop here because we ran out of time, but I'll come back here and explain this issue next time. Okay, then I will see you on Wednesday, and have a good evening. Good luck with the rest of your classes. Good luck with my midterm actually. So that's why I'm not teaching tonight. So whoever is in my class has a day off and they work on the midterm. Okay, thank you.